Welcome to 10 minutes CS. 458 Height of binary tree after subtree removal queries. This question is previously asked at Google and is marked hard on Leetcode. Though it's hard marked, but still I feel this question is very intuitive and it's really good in terms of the data structure used, and it's purely based on logic rather than other questions where you need to have to know that particular algorithm to decode it. So let's see what the question says. You are given the root of a binary tree with n nodes. Each node is assigned a unique value from 1 to n. You are also given an array queries of size m. You have to perform m independent queries on the tree, where the ith query you do as follows. Remove the subtree rooted at the node with the value query I from the tree. It is guaranteed that query I will not be equal to the value of the root. So the question says we are given m queries, and in each query we are given the node value, and we have to return what will be the height of the tree after performing the ith query. So at ith query we are removing that node from the tree and then trying to find out the maximum height of that tree. And each query is independent. That means after removal of that, after once we have done that query, the tree goes back to its initial stage. So the height of the tree is the number of edges in the longest simple path from the root to some node. So let's say we haven't performed any query yet. So the simple path which is the longest is 5, 8, 2, 4, which is 1, 2, 3. So the maximum height of this tree is 3 in this case. And one more important thing to note here is each node is assigned a unique value. So that means there are no duplicate values. Why this is important here? Because at query I we are giving the node value. If there are multiple nodes in the tree, we will not be able to find which node to remove. Let's say there is an 8 node here and there is another node 8 here itself in the right subtree of 1. So we won't know which 8 that is asking for being removed. So let's try to dry run on this example. So here the first query says we have to remove 3 from the tree. So if we remove 3 from here, so the maximum path will be 5, 8, 2, 4. So that is 3. This path 1, 2 and then 3. Let's go to the next query, that is 2. So if we remove 2 from here, then the maximum height of the tree will be either this, which is also by going to that path we get 2, and with this path also we get 2. So that is we will get 2 here. Now for 4, the fourth node is here. So if we will remove this, we will still get 3 as by following the path 6, 2, 8, 5. So this will give us 3. Now next is 8. So if we remove 8 from here, the maximum height that we can get is 5, 9, 3. That will be 2. Height is the number of edges. That's why we get 2. Let's observe how we are able to conclude the answers here. The first approach that we can go for is we can find the length of the height of the binary tree after uprooting. So each time we can go ahead and remove the node from the tree and then can run again a DFS and find the maximum height. So each time we will be doing 2 passes and we will be checking for the height of the tree. That will be a lot of computation and will give us a TLE. I will recommend you to write this approach and see, just for your practice. Now definitely we can't go again and again and uproot the node and then can find the height of the tree. So definitely we have to do some pre-computations. Now one thing we noted here is, let's say we remove this third node. At that time the maximum height of tree was not affected. It was only affected when the node that we uprooted was the part of the maximum height. and in that case we have to find if it is removed, then what is the next maximum height that we can get. As it is a binary tree, then definitely we can only have the maximum heights from the left part of the tree or the right part of the tree. So first thing we can do is we can try to compute the height of the tree from the left side and the right side. So we can have either two arrays, left and right, and left and right. But what will be the length of this array? We don't know unless we go ahead and check for the maximum number of nodes that a tree can have. Here we see the maximum n can go is up to 10 raised to the power 5. So we can have one array such as 1 into 10 raised to the power 5 plus 1 length, or we can use a map. While in interviews, we usually not given the constraints, so we don't know the value of n that it can go. It is very helpful if you are given an OA, so you can go ahead and check for n and can assign or initialize the array based on it. Here we will do it using a map, so we do not occupy some extra spaces which are really not required, because let's say for this example only we are given nodes from 1 to n, and if we have initialized our array with this, there is a lot of extra space that is being computed, being initialized but not used. So let's go with a map. So our left and right are maps, and what is the key here? Key is the node value, and the value is the height of the tree. So let's go ahead and try to populate it. Using the same example, we go ahead and check for the root node, and then we can go to its left node. Now our left is not null, so we'll go again to left, and then we go to left. Now the left is null here. Whenever we reach null, we can return 0. So the height is 0. So if our node is null, so we can return 0. Similarly, then it will go for its right, so this will also return 0. So we have to go to two sides, so our helper function will go to its left and will go to its right. Node.left and node.right, and we get our left and right values. Once we have got that, we can assign it to our map. So our map got assigned at 4, left is assigned as 0, and at 4 right is assigned as 0. Now while sending back the query, it will get the maximum of both the sides and add 1 to it. Why adding 1? Because this extra edge will be added, or the depth will be added. So here R2 got 1 from its left side, and here then it will go to its right node and check again. So here we got null from each side, so it will be 0 0, and from right it will get 1. Similarly, we will keep on going back and keep on populating the R tree and the map also. So here we can add it our map left dot put our node value and the left height, and similarly we can do for our right. So here we will get 2 from this side, 1 from this side, and it will go check the maximum is 2 plus 1, so that will be 3. Now it will go to its right, it will get 0 0 from each side as it will be null, and it will go ahead and take the maximum of both and plus 1, so it will be 1 here and then 1 here, maximum of both 1, and then add 1 to it, so it will be 2. Now we know what is the maximum length that we can get from the left side and the right side. The other thing is we now can go ahead and check for each query and can uproot that node and check for the height. But again, if we will do that same thing for each query, that will give us m into n more computations, right? So let's pre-compute at first itself what happens and what will be the height of the tree if we have uprooted each node, so that when we are going through our query array, we can take help from that. So again, for storing that pre-computation, we will need a map. So let's store it in our map height. And now how will we add it? So a simple expression that we can use here is, let's think of a scenario when you are removing the left node. So if you are removing the left node, then your height will be coming from the right node. So our helper function, if we are removing our left node, that is the node that needs to be removed, so our current maximum, that is the maximum height, will be coming from its right node. And how will we know what will be the maximum height from the right? We can check it using our right map. So from right map, we will take our root or nodes right. Now let's go ahead and check for other nodes. Now we go ahead and check for this node. Let's take this second node 2. Now if we have removed this node, so either the path or the height from this side will be the maximum, or the height that we get from this path will be the maximum. So how will we compute this path? So we can take that same recursion call. So if we have removed the root.left, so either our current maximum we can keep on sending to our function call. So either our current max will be the maximum, or the depth that we have till here plus our right node will be the maximum. So what we have to send here? So we send the node, that is root.left, and we check for the maximum of our current max and the right node plus the depth. So we need to pass depth also as one of the parameter. Similarly, we will do for our right. So when we are computing for right, we check the max of the current max and our left side. So let's say we have removed the right one, so either we will get the maximum from the left or the current max. So left, so root dot value, so here it will be value, and we will pass depth +1 each time for the next call. And the initial call will look like, for our left, root.left, and our current maximum will be from our right left value with depth as 1. Similarly, we will go ahead for our right also. Let's do a dry run for better understanding. We are given in the question that there won't be a query when we are removing the root of the tree. So let's call for the left side of the tree. So first of all, we are at node 8 and we will call with the current max. So when we are removing the left node, our current max will be the right, so that we can get from our right map for this particular node. So right of 5 is 2. That's how we will get the 2, and depth will be 1. And we will update our 8th node map with the current max, and then we will call for its left tree. Now here we will now our depth will be updated by +1, that is 2, and our current max will be updated with the maximum of our current max with the right of that node. So we will take it from our right map. So right of our 8 is 1, so max of 2 and 1 is 2, so we will pass 2 here, and depth is 2. And again we will update r2 with our current max, so that is updated here. Now we'll call for the next call. Now our depth is updated with 3, and our current max will be updated with our current max with depth plus the right of the node. So 2 plus 1 will be 3. So then now we will update our 4 node with its current max, so this will be 3. Similarly for this call we will get 3, and we will increase our depth to 3, so 6 also will be updated to its current max. Now we'll trace back and go to its right node. Now here we have a max of current max or the depth plus the left. So 2 plus 1 is 3, so current max will be 3, and for the next iteration we have updated the depth, so 1 will be updated to its current max, that is 3. Now we'll go to the right side of the tree, and we will pass depth as 1 and current max as the left tree's height. So we will update 9 to our current max first, and then we will go for the left call. Now the current max for this one will be max of 3 or its right, that is 1 plus 1. So max between 3 and 2 will be 3, so this is updated to 3, and depth will be updated to plus 1, that is 2. So we will update our 3 with a 3. Similarly here also it will be 3 and 2, so we will update our 3 to map of 7 with 3. So this is how it will look finally. And for the queries, then we can run a for loop for our queries, and for each query we can check in our height map. So our queries were for 3, 2 and 4 and 8. So we see for 3 it is 3, and for 2 it is 2, for 4 it is 3 again, and for 8 it is 2. So this will be the output. For this we just take let's look at the code. We are given the root node and the queries array. So we initialize 3 maps. First one will be the left heights, right heights and heights after removal. Then we populate the right and left heights. We will see the code for this function also. And then we go for populate heights for our root left and root right. So the one that we did in the previous dry run, we go for left tree and the right tree. And while doing that, we update our current max. For the left node, we will take the right height for that root value, and for right, we take the left height for that root value. And then the depth will be 1 initially, and we will pass our all 3 maps. You can also keep these maps as a global variable, so you need not to pass it for the functions, but I mostly. And then finally, when we have done it, we can just run over the queries, and we have the heights after removal for that particular node. We can get it from our map and can update it. So here also you can either create a new array and update it there. I just updated in the input queries only and returned it. So let's look at the populate right and left height function. We are passing here the node and our maps. So if the node is null, we just return 0, else we will calculate the left and right height. For left, we pass node.left, and for right we pass right node dot right, and each time we update it in our map and we check what is the maximum between our left height and right height. We'll add 1 for it to account the edge and then return it. Now let's look at the another function where we are doing the computation for populating heights after removal. We pass node, current max and the depth, and all three maps. So if the node is null, so we need not to do anything and we can just simply return, else we will update our height with our current max, and then we will go for our left and right subtree. While doing so, we update our current max depth with our current max depth, or the depth plus the right if the node is left, or for the right subtree we updated with depth plus left height and the current max. Each time we have to update the depth with +1. So overall our code looks like this. We have the tree queries function. We update our right and left trees, left heights, and then we populate our heights after removal for our left and right subtree. Let's submit this code. Yeah, indeed it's passed. So let's analyze its time and space complexity. Here if we see in populate right and left height, we are going through all the nodes just once. So it will be O of n if n is the total number of nodes present in the tree. And for populating heights after removal, for that also we are going over each node once. So this will also be big O of n. And we take 3 maps, and each map has n number of entries. So each map will be big O of n. So total space complexity will be 3 times of big O of n, that is approximately equal to big O of n. And for these functions, that will be twice of big O of n, that is also big O of n. And then we have queries which is big O of m, so that will be n plus m. Hope you like the video. Thank you for watching.